Hi, my name is Sudama, and at this week's challenge, we will be making a rectangular path with a robot, making it trying to go in a straight line, pivoting 90 degrees, and then going again and again pivoting. And the point of this exercise is to find out what's the most reliable way to ensure that the robot can make repeatable and accurate trajectories, especially when it comes to turning. Last week, we tried using encoders to track the distance, which was pretty good, as we can calculate the number of encoded ticks on both the front left wheel as well as the back right wheel, and that lets us know if there's any wheel slippage or if one motor is moving faster than the other, and we can compensate with that by using a proportional controller, and we can make sure that both the wheels are rotating the same amount, and we can ensure that the robot is going in a straight line. But in the case of turning, we cannot use the encoder ticks for one main reason that comes up in our situation is wheel slip. Since we're calculating the number of encoder ticks, we can calculate the number of ticks required to make the robot turn in a certain way in an ideal situation, but we don't live in an ideal world, and we get wheel slippage as the wheels try to gain traction on one side and the other side also tries to gain traction, and that creates a lot of friction in the ground, and that causes wheels to slip and false encoder readings. To compensate for that, we have an IMU, an initial measurement unit, and this sensor has a bunch of additional sensors on it, including a gyroscope, accelerometer, magnetometer, and all in all, what we can do is we can now find the true heading angle of the robot, making sure that it follows the trajectory that it's been assigned. And there is some trial and error that's required in this as well, but once you dial it in on the surface that you are trying to operate the vehicle on, it's pretty good. For this, we also use a proportional controller for this to ensure that when the robot starts turning, I've given it a maximum duty cycle of 100, which is the motor limit, and a minimum of around 30, so that when it starts its rotation, it can start fast, but then as it gets closer and closer to the target goal, it starts going slower. So that's where the errors becoming slow and errors becoming smaller. So the proportional constant being multiplied in depth to give you the become smaller as well. So it starts to slow down and until it reaches its goal, and then it starts going ahead. And that's so using a combination of both the encoders as well as the IMU, we are able to get pretty reliable results.